Okay. Couple of important announcements before we get too deep into things. The first is, I haven't really done a good job of announcing this, but we have an exam a week from today.
Oh.
Last exam in the class, thankfully. There's no final and there's nothing that's, there's no final. Yeah, the last exam in this class is going to be next Friday. And the plan is, so we're covering the last material for that today and possibly Monday. We'll see how that goes. That is very loud. So that's the plan for that. The second is that there's been a pretty significant challenge of getting our singly linked lists quicksort to be log linear. If you implement this while calling any of your existing linked list methods, at least in a singly linked list, since there's that find node before, you find yourself very frequently getting yourself in a quadratic situation. So one way to test this that has been successful so far is to make a linked list of size 1 million and fill it with random stuff. I like to fill it with random doubles. So you just make a random object and fill it with random or whatever you call your random object dot next double. It'll give you some double between 0 and 1. And then have yourself go set the sort of your singly linked list object to the quicksort and actually go run that and see, print out something after you've made the array, print out something that says starting, and then have it sort. And when it's done sorting, have it print out done sorting. If it finishes in, let's call it within 20 seconds, then you're good. That's log linear. If it is sitting and sitting and sitting and sitting, and after 20 seconds it hasn't finished, it probably should be well under 10 seconds, but I'm trying to figure out the worst performance that I could expect in the class. So maybe if there's some extra constant factor in there, maybe it's 20 seconds. But yeah, if it's quadratic, it will not finish in that period of time. And that will tell you that there's something going on that is not log linear. So the way you're going to have to get around this is to kind of reinvent quicksort a little bit. So let me draw out an example that I've been using in my office. So we have some singly linked list. I should have started this well over there. So I've been using the example of we have a pivot, assuming we're starting the pivot on the first element. We're going to have something that is greater than the pivot, less than the pivot, greater than the pivot, and less than the pivot. And it doesn't really matter what these values are. You can see that if we're trying to do a quicksort on this, that we need to do some swaps to get these values over here and these values over here. Has anyone figured out a log linear approach to doing this? What do we think? Yeah. Not really, because when we start low or whatever it is that we want to call it here, and we start high here. How do we bump down high? We have to call find node before. How much work is that? Because we start at the beginning of the list to go do that. So we're going to have to iterate all the way to high. Then when we bump it down again, we're going to have to start at the beginning all again to get to the next one and the next one and the next one. And you can see that this is a 2D structure. If we're trying to think of the area that this is representing, it is quadratic. It's kind of a triangulation based on the size of this list. So that's an issue. That implementation is going to be quadratic in nature. The solution I came up with for this was we are going to make a single pass through this list from start to end. Starting at low, we're going to ask, all right, is low greater than or less than the pivot? Since it is greater than, the first thing we're going to do, well, I guess first we should say, since this list is 5 elements, we want to do something 4 times. So the length of this list minus 1 times we're going to look at the next element. When this element is found to be larger than the pivot, we are going to now, instead of waiting to swap, we're immediately going to insert this node at the end of the list. And then we are going to delete it from here. So that is the equivalent of the garbage collector will come eat it. But as you do this, what you really should have stored is probably some kind of a previous and a current. So this would have been your prev, this would have been your cur. Now that the cur has been manipulated, before you delete this, you say cur equals cur.next. Since we made a change, we don't want to change prev. If we didn't make a change, we would want to update prev. So now that cur is here, prev is here, we ask is cur less than our pivot? It's not. So we bump up both prev and cur. So prev is going to point here. Cur is going to point here. And you make a note that I made one change. All right, now is cur greater than the pivot? Yes, it is. So we're going to, before we do this, we're going to say insert cur at the end of the list. And we know that adding at the end, since we have a tail reference, is not linear, it's constant. So we're going to add 31 to the end of the list. Luckily, this is the last thing we're going to have to do. And then we say cur equals cur.next. And we can now delete this node prev.next. So we just redirect prev's next to point to cur. That effectively removes this. Now we have what ends up to be a sorted list, but we don't actually know for sure whether this first half and the second half are sorted with respect to each other. But we then ask again last time, because this is up to the length of the list -1 4 times, is the 2 less than greater than the pivot? It is. Since it's not, we're done. And we add in one more change that we made. The number of changes that we made tell us the index where the pivot is supposed to go. Since we made 2 changes, the pivot wants to go at index 2. So you can update the value of cur to be the pivot. Since you're doing this once, it's okay to do a linear operation once. You just can't do a linear operation some number of times proportional to the length of the list. So as we do that, we really want to swap the 20 with the 2. So finding this 2, hey, it's already what cur is pointing to. Is that guaranteed to be the case? Yes. Great. You swap pivot with cur. This becomes 2. This becomes 20, and then you would call your quicksort on the first half and the second half. So we know the 20 is in the right place now. So this is an equivalent quicksort. It's still using the same algorithmic process, even though the exact underneath the hood mechanic is different. There's no low and high. We just make a single pass, taking everything that is larger than the pivot, moving it to the end, and then deleting it. Every one of those operations is going to be constant because we're making a single pass through that. So we still get a log linear outcome. Question?
And then in the partition we're returning, would that just be the index for H?
Index for H.
Or just H?
Yeah, we'd be returning, yeah, this cur, this H doesn't really exist in here. So we'd be returning the index of cur. And we would be returning the number of operations that we made as that index. So this is index 0, 1, 2. Whatever we got rid of when we went through and did that, however many times we did that, that is going to represent the position that the pivot needs to be in. Question?
Not to make the center class or sort of you put it in the symbol list.
It should be, that's the other important point, is that I updated the write-up, I think on Monday, a little bit to say it should be in a separate class. So there are a couple changes about the the structure of things to make use of what we've done. So let's actually just draw that out real quick. We had our list interface with our associated list objects. We had our singly linked list, etc. We had our sort interface. And we had our different sorts. We had bubble sort, etc. So all you're doing for this is you're adding two new classes. You're adding a merge sort. And you're adding a quick sort. The only other potential change you would need to make is within your linked lists, wherever you're calling your set sort or your equivalent. Now there are a couple more options for what those sorts could be. There's a merge sort and a quick sort. If you've done any work to eliminate that, maybe you've made an abstract list class that tries to abstract all of this higher up. There may not be any work that you need to do whatsoever. So we just need something, some kind of sort. If you implemented this generically, then adding a merge sort and a quick sort just now become options to pass to set sort. So really nothing should need to change. If you have designed this well, by writing these two classes, none of this other work needs to be modified. Just please make sure that both your merge sort and your quick sort run in log linear time. That is the important part. If you implement a quick sort that does not run in log linear time, then there's no benefit to the quick sort. You might as well have implemented the bubble sort or the insertion sort or the selection sort. Yeah. They were log linear on an array because we could easily find the previous element. And if you do it for a doubly linked list or a circular linked list, they can also be log linear because we have an easy access to a previous element. It's only in a singly linked list where to get access to the previous element, we have to call find node before, which is a linear time operation and not a constant time operation like with a doubly linked list, just calling a node's previous. So it's only for the singly linked list, but because this is structured the way that it is, a singly linked list is one of the options that we could pass in to tell it to sort. So in that case, if we were calling quick sort on a singly linked list, if we did exactly what we did in class, then it would be quadratic. So that's why this is required for the singly linked list. And since we've done this generically, this will work for all of your linked list types and be log linear for all of your linked list types. Yeah.
You have your own principles in the place.
Yes. Yeah, I'm not too concerned, but you really shouldn't need to modify too much with your list. If what I've seen that's useful is to make an abstract list class underneath the interface, so kind of between the interface and the actual lists. And that way, anything you duplicate between these lists, if you copy and paste anything, like the set sort method, for instance, was basically copied and pasted among your 3 different list types. So you could throw that in an abstract class and then just have 1 copy of it rather than 3 copies of it. Yeah.
I ended up down a hole last night, ended up making an interface for node to an abstract there, so what was that? Okay.
Yeah.
It's not necessary.
Yeah, it'd be fine, as long as there's reason for whatever you put in that abstract class. I'm not super worried about the exact design, as long as we have the ability, as long as it still adheres to the strategy pattern, which even if you write abstract classes for any of these other things, it will. And what we care about really is the performance. Merge sort and quick sort are the better sorts because they are faster. So we should make sure that our implementations are actually faster. So the other thing to be concerned with is if you call any get or update, these for a singly linked list all start at the head and all go as far as needed in the list to get there. So this is a linear time operation in your list. If you do this once, that's okay in a sort. If you do this for each element as you're walking down the array, that's where it becomes an issue. Something that is linear times some proportion of the length of this list ends up being quadratic. And when you have a list of size 5, not a big deal. When you have a list of size 1,000,000, suddenly it doesn't finish today. You have to wait days for it to finish and not seconds. Maybe hours. Questions? I hate doing this the day that it's due. If this becomes an issue with your schedule for the day, please just reach out to me. I can extend it a little bit. I just don't want people to get too far behind. And what I'm really trying to do is have this class have no work the last week of class. That's the hopeful idea, but that also does leave a little bit of room for if things need to be extended for your own schedule, I can work with that. So let me know if it's an issue, but any other questions on this process or why this process is necessary just for the singly linked list? Right. I think we're good. I will also reveal your next assignment today. I don't yet know exactly when that will be due. I can probably make it that last week. I don't really want there to be overlap between worrying about an exam and worrying about an assignment. So I can give you a while to work on this new assignment. Last time, we were talking about binary search tree traversals, and we basically finished binary search tree traversals. We talked about 4 different types. There was the pre-order traversal, post-order traversal, in-order traversal, and a level order traversal. The first 3 were naturally recursive. They're all 3 lines of code if you implement them recursively, and then the level order is not. Level order required a queue object and going through that process. The last thing we might want to do for a tree is to search it. So a contains method would just be able to tell us if a particular node exists with data equal to the query. And this could just be, if it's a binary search tree, that would be great. But now we're going to remove the assumption that what's stored in the tree is sorted. That means that we can't query, is it less than the root or greater than the root? We have to actually fully search the tree structure to figure out whether this is contained in the tree. Usually, if it is possible to sort elements within a tree, that is a great idea because it will minimize the amount of time that it takes to do this. But not all data is inherently comparable. Not all data is inherently easily searchable like this. And so there are a couple algorithms you should be aware of if your data is not sorted. So the first is called a breadth-first search. Who's heard of a breadth-first search before? A few people. So a breadth-first search is really just a level order traversal. We're going to be looking at every node in the tree that is at depth 0, depth 1, depth 2, depth 3. And for every node that we visit, we're just going to say, is your data equal to the query data? If it is, output it. If it isn't, keep looking. Make sense what this algorithm is doing? Level order traversal looking for a particular value. Benefits of this: we don't actually search deeper into the tree than is necessary, which also means if duplicates are allowed in the tree, it's going to give us the shallowest copy of this value, which may be particularly useful. Imagine that you are trying to figure out the fastest way to get from the Catalyst building somewhere else in Spokane, and you're using Google Maps. There are lots of different ways that you could get from point A to point B. And that's nice because we're on the West Coast and we have a grid as opposed to East Coast cities that there's only one way to get to your destination. Sorry, any chance I get to bash the East Coast, I will. So this is nice. If you're looking for the shortest path to there, you don't want to learn the shortest path between here and what's a common destination? Spokane. Spokane Arena, why not? The shortest distance between here and Spokane is drive east on I-90 for 264 miles. Turn around, drive west on I-90 for 264 miles. That'll still get you to Spokane Arena, but it's not the way you want to get there. So because of this, it will return the shallowest node, the shallowest way with the fewest connections to actually get to that node. So because of this, you can think of it kind of like keeping track of a horizon. By the time we've finished a depth first search, iterating on depth 1, we know that if we haven't found that path, maybe they represent miles, then there is no 1 mile path to get to Spokane Arena. By the time you finish depth 2, there is no 2 mile path to Spokane Arena. Cons to this approach? Well, the queue that we are using to store this data, we saw this in our example of this yesterday. As we explore another level and another level and another level, what's in the queue is growing. Because when we finish a particular level of the tree, the entire next level is in the queue. Let's draw that out so we can see it happen. We have some really small, but when we finish this level 1 approach, then all of these nodes in level 2 are in the queue. But how many nodes are there at each successive level? Double the last one, double the last one, double the last one. It's exponential growth. So the memory requirement for breadth first search is exponential based on the height of the tree or the depth that you need to get to find your query. And that is a huge problem for large trees. So that's a pretty big deal. Questions on that concept or the major con of breadth first search? For large problems requires too much memory. That queue just gets larger and larger and larger and never gets smaller until you happen to find the answer. Time complexity? How long is it going to take to find a query in breadth first search? Based on the number of nodes in the tree, based on anything else that we care to measure? We're only processing each node once. Once we process a node, we just ignore that it exists because when we didn't find it, there's no reason to search it again. It's pretty linear. With respect to the number of nodes in the tree. What about with respect to the depth of the tree? Comparing depth 3, in the worst case, how many nodes do we need to find for a depth 3 tree? Quick mental math. Depth 0 has 1 node. Depth 1 adds 2 more for a total of 3. Depth 2 adds 4 more for a total of 7. And depth 3 will add 8 more for a total of 15.
Would be.
How does, yeah. So it's exponential with respect to the level of the tree, which is what we see kind of when we have the memory out there as well. That's exponential in terms of memory. So if you're asking how many node comparisons would we need to do based on the depth of the tree, well, it just tells you that there's an exponential number of nodes in your tree, not really anything about this algorithm in particular. What other important considerations? So the next searching algorithm that we might want to use is called a depth first search. So depth first search, instead of using a level order traversal, we'll use an in order traversal. So remember that in order, if the nodes in the tree are sorted, prints them out in order. So it has the same definition of visiting as with a breadth first search. We're going to look at whatever node depth first search tells us to look at next. And then we're going to ask the question, is this equal to the query? Is this node's data equal to the query? If it is, we return that node. Great, yes, it's in the tree, it's right there. If not, then we have to keep searching. But with in order, we know that what happens is we kind of pick a direction and we just go. If this is a binary tree, then we pick the left child, left child, left child, left child. The very first node that we visit is the deepest, farthest left node in the tree. Furthest left node of the tree. So compare this concept to breadth first search. How do the pros and cons differ? So now instead of going level order, we're going all the way and kind of doing, if you remember that 15 node tree, we were visiting them in the order of low to high. What does that change about the guarantees that breadth first search gave us? What does that change about the benefits or detriments that breadth first search gave us? Yeah,
So it takes less, memory, but also take longer.
it takes less memory. That is absolutely true. Are you guaranteed to return the lowest depth solution in the tree? We are not. Let's draw it out a little bit. I'm only going to put a couple nodes to make this large enough to visualize something. So let's say here is a 3 and here is a 3. If we did this with breadth first search, we would be doing this level order. It's not here, but hey, look, we found it when we were iterating through this level. With depth first search, we just go left, left, visit. We find this 3 and not that 3. But we found that when we visited these two nodes, the queue had 4 nodes in it. With depth first search, you really only need to keep track of and have memory for the amount of memory that is in this linked list of how many connections are there between the root and the deepest node in the tree. That is the most memory that you will ever have needed at once. And what's nice about this is even for a depth 50 tree, that's only 50 nodes. How many nodes would be in the queue after we parsed depth 49 if we had a depth 50 tree? Something on the order of 2 to the 50th. 2 to the 10th is 1,000, 2 to the 20th is 1,000,000, 2 to the 30th is 1,000,000,000. So 50 versus 1 quadrillion nodes. We do not have any kind of memory like 1 quadrillion of anything. So using level order traversal, we would not be able to store a depth 50 tree and parse and search a depth 50 tree. But with depth first search, we easily can. What about the time? Is it going to take more time? Same time? Less time than breadth first search? Yes, same time. So the only con of depth first search is that it's kind of picking a direction and going. This is like saying, all right, I'm going to search for Spokane Arena, but I'm going to start out by going east. That's not going to go so well. There's a lot east of us that is not Spokane Arena before we backtrack all the way back to here and say, let's explore north instead. Let's explore south. Let's explore some other direction. And there's a lot that's going to be in that direction. We have to decide, well, we should probably do west and a little bit north. There we found it. But when we start going east, we're going to continue going east until we hit a dead end. There's a lot east of us that is not Spokane Arena. So it picks a direction and just decides to keep going that direction. And in a really large structure, that can lead you very astray. And when you do find a solution, maybe there is a building called Spokane Arena in, I don't know, Atlanta, Georgia. If we decide to go east, we're gonna find that Spokane Arena before we find the Spokane Arena that's a couple miles away. So again, we get that guarantee that it's not the closest one to the root.
Are binary search trees always sorted?
If they're a binary search tree, by definition, yes. If it's a binary tree, then not necessarily. If it is some tree that is not necessarily binary, then also no. So a search tree is meant to be ordered in some capacity. Great question. So pros of this. Memory proportional to the depth of the tree rather than the width, and the width grows way faster than the depth. Cons of it is no guarantee that when we find a solution, it is the shallowest solution or the closest solution to the root. Complexity of this, we see that it's linear in terms of memory instead of exponential in terms of memory, which is wonderful, linear based on the depth of the tree. And in terms of time, we're still just at the most looking at every node in the tree. In fact, if it is the deepest rightmost node in the tree, regardless of whether you use breadth first search or depth first search, it's the last node you'll go look for. Of course, you could do another kind of traversal that is not common at all and do, instead of a node left, or sorry, a left node right, you could do a right node left. And that would, instead of going all the way down the left subtree, that would start by going all the way down the right subtree. Because we read left to right, we program searching structures from left to right. But there's no reason that we do that other than that's what's natural to us. It is perfectly computationally equivalent to start from the right and look to the left. All right, that's the end of everything we have on trees. We feel ready to go make one of these structures for homework. There'll be a little bit to look back over, but luckily it should be pretty straightforward compared to a lot of the stuff that we've done in class. I'm sure I will be fielding plenty of questions as we move. So next thing we're going to go look at is heaps. You'll see on the study guide that I will only require you to know about heaps. We'll not need to implement heaps in any capacity, but we're going to implement one in class for fun anyway, because you will need to implement one in algorithms. So maybe it will be useful to look back at this as a, what were heaps? Oh yeah, we covered that in data structures. This is not typically, we've kind of reached the end of the curriculum. Binary search trees are the end of what I am required to cover in this class. Everything from here on out is to make algorithms easier on you. So trees are great. In fact, they're more widely used than just for searching. One kind of tree is going to be a structure useful in many situations, and we're going to look at what a heap is and what it can do for us. In fact, it's yet another advanced sort, as we can use it heap to sort things. But there are also many other uses for heaps. So heap sort is an advanced sort that runs in log linear time. After we make a heap structure in class, we will actually just write a very quick heap sort, because given that we have the code for a heap sort is actually incredibly efficient in terms of the number of lines that it is as well. There's also a concept called a priority queue. And this is like a queue, except instead of removing the element that has been in there the longest, each element, when it is n-queued, has an associated priority with it. You can think of this as like an email has a priority, or maybe your daily task list has a priority. You can imagine that how you make decisions today is based on, all right, I need to do whatever has been around and on my to-do list longest that has the highest priority. So you look through your list of tasks and say, what haven't I focused on that has high priority? And you're only going to get to a medium priority task once all of your high priority tasks have been accomplished, even if that medium priority task has been in your to-do list for a month. So you would think that you could use a queue to do this, but unfortunately, searching a queue, since a queue is stored as a list underneath the hood, is linear. If we can find a way to utilize a tree, then figuring out what task to do of the highest priority can actually be logarithmic. Rather than linear, which is a huge speed up. So that's why we use a tree-based structure and a heap to do that. So we're going to define a max heap, and then we're going to implement a min heap. Has anyone heard of a heap structure before? Hey, a few people. Where did you hear that? I'm curious. Instagram? Cool.
See. Probably see.
All right. So we have a tree structure, but we're going to add some restrictions. Just like a stack and a queue were restrictions on a list for what could be done, a heap is a restriction on a tree. And with that restriction, we can start to speed up some other tasks that we would want to do with lists or trees. So here are those restrictions. Every parent in the tree is greater than all of its children. So this is not a search tree. This is not a tree that has sorted order. So every parent greater than all of its children. Where is the largest node in the structure? The root. Yeah. Where is the smallest element in the structure? Some leaf somewhere. Do we know which leaf it is? No. Could be any leaf. Every level of the tree, except potentially the last one, is full. This means that we can't get a structure that looks like this. This is not a full tree. Well, it technically is, except for the last one. Let's say we'll go one more. This is not full because there would be places for children there that are not used. So a full tree is as shallow as it could be to store that much information. If that makes sense. And that last level, all of the nodes are as far left in the level as possible. I think I actually go to this. Let's go ahead and just say real quick, give yourself a minute or two, make a legal heap. So draw some kind of tree structure and have it adhere to these rules. Legal heap? Yes or no? Yes, it is. Every node is greater than, every parent is greater than its children. 70 is greater than both 63 and 4. 4 is greater than 2. 63 is greater than 17 and 26. Ignoring the last level, this is full. Every possible child of the root has a value. And in the last level, everything is as far left as possible. This would not be a heap if this 2 were a right child of 4 and not a left child of 4. It would not be a heap if the 2 were here, the 26, and we found some way of doing that. If this were large enough that we could move 2 elements here and a single element here. So it's all the way to the right instead of all the way to the left. Also not a heap. By some other definition of a heap, you could actually make that work. But we're going to say all the way left. Questions on heap rules? Did you try out something that looks kind of like this? Hopefully.
What about if you swap the 4 and 63 on the second level?
That would not be a heap because these values would be larger than their parent. Not allowed. So there's nothing that says that this value has to be larger than these values, it just has to be larger than its descendants. Which is why I chose kind of extreme values here, was to make that point clearer. All right, so that's a heap. Next question I would have is trying to access the largest element in the heap. We already asked, where is it? We found that it's at the root. And what's nice about the root? How fast can we access the root in a tree? Very, very, very quickly. Constant time. It's one of the fields in our tree structure. So, visualizing it as a tree structure, it's really funny that despite visualizing it as a tree, the structure we use underneath the hood is actually a list. This is very counterintuitive. But we're going to say that the keys for all of the nodes are stored in the list in level order. I should have left this up there. I'm going to draw it again. So if we were drawing this out as a list that had some number of indices, one too many, but that's okay. Again, we had 70, 62, 4, 2, doesn't matter what these are. I'm gonna call this 36 and 17. I don't know if that's what I had, but those numbers sounded familiar. So we would store in this array or list, whatever we want to call it, we would store 70 here, 62 here, 4 here, 36 here, 17 here, and 2 here. So again, in just level order. So this is the actual programmatic structure that stores this idea. If we want to visualize what's going on, draw it out like this. Internally represented, it's going to look like this. And we will see how they're equivalent here in a moment, at least for this structure. Now I ask the question, given a node's index in the list, where is its parent? So I query, what is the parent of 4 in this list? Where is it in the list? But now, in general, what is the formula for given a node, where is its parent in the array? Yeah?
Like with the first step, just look for things that are larger than it, if you're looking for the parent.
Would that work? 17 is larger than 2. Is 17 2's parent? No. It's a good idea. So thinking about 2 wants to map to 4. 17 wants to map to 62. 36 wants to map to 62. 4 wants to map to 70, and 62 wants to map to 70. So that's the entire sequence. We need some function where if we applied that function to each one of these indices, we would get the associated index where this arrow is pointing. What is that formula? Yeah. It is not quite that complicated. But it's a good idea, yeah.
You would take the depth level. So for 62, it's 1 depth away. And then for 4, you would have +1.
That's also more complicated than necessary. What's the simple answer?
All 2 of them.
That's close. It's just integer divided by 2. So integer divide 5 by 2, you get 2. That's where that points. Integer divide 4 by 2. Uh-oh, that's a 1. So it's close. So we need to subtract 1 divided by 2. So we're going to take the value. So index minus 1 over 2, integer division, and that's going to be the index of the parent. Questions on that? Does that make sense? Does that map to the logic of where these arrows are pointing? All right. Given a nodes index, where is its left child? Yeah, so we're looking for a left child, so 70 should point to 62, 62 should point to 36, 4 should point to 2. So if we're redrawing these arrows. 70's left child is 62, 62's left child is 36, 4's left child is 2, and nothing on the last row has a left child at the moment. So how do we make that consistent? And what would be consistent if these did have left children? Times 2 plus 1, I like it. Actually, I'm going to draw this here. This was. See it. We need the parentheses there, but gives you a sense of multiplying and adding. How about given a node, where's its right child? Yeah. Wherever the left child is, the right child is always one index higher than that. So we take whatever this is and add 1 to it. So this is just index times 2 plus 2. So now we have a full representation of this tree structure. We can apply this formula to do anything that we would want to do in a tree. Whereas this node's parent, we have an expression for that. Where is this node's left child? We have an expression for that. Where is this node's right child? We have an expression for that. So with these 3 formulas, we have an equivalence between this structure and this structure. And the reason we do this instead of this is that array indexing is constant. Tree searching is logarithmic. So by storing this here instead of here, we can actually query some things about this if we know more in constant time rather than doing a tree-based search. So this is just a nicer way to do this. And with these formulas, we embed this structure inside of this structure. Yeah.
Can we only store it in the list and have those constant time operations due to the restrictions placed on this tree?
Yes.
Okay.
Or at least rather it makes sense for, it wouldn't save us anything for any other tree-based structure to actually store it in a list, and it will actually save us a little bit of time for it. Okay, we have just a couple minutes. Let's see if we can do something with that. We'll see if I can get away with leaving this up here. So how do we insert into a heap? We have an existing heap, and now we want to add a value to it. So what could we do? If the last row is not full, we ask, is the leftmost element null? It is the leftmost null. Is the leftmost null? If it is, then we can just insert it there and deal with how do we modify the heap to make it legal. If it is full, we'll make a new row and insert it in the first position. That should say first position. Let's just say leftmost. And of course, when we do this, we violated some heap rules. Let's say I wanted to insert 100 into this heap. According to this rule, we would want to put it right here. think of the shallowest leftmost position that it could go, which is going to be right here. If we insert 100 right here, we violated some of the heaps rules. We no longer have a legal heap. What can we do about this? The solution, I'll just introduce it really quickly and then we'll draw this out at the start of Monday's class, is we are just going to continue to look at, should we swap it with its parent? In this case, yes, we should. So we swap the 100 and the 4. Recurse, should we swap it with its parent? Yes. Legal heap? Yes. Will that always be the case? Yes, it will always be the case. So just compare the current node with its parent. If the current node is greater than its parent, swap. Continue to do this. Will it always produce a new legal heap? The answer is yes. The complexity of this is logarithmic, since we're making at most one swap per depth of the tree. So it is a nice logarithmic insertion process. We'll come back and look at this again at the start of Monday's class and get into deletion and actually writing one of these, coding up one of these to see how it works. See you Monday, look for a study guide later today.